This is the third and final lecture of second week, and this week in this lecture we are going to talk about decomposition analysis and parametric approach. In the previous lecture we already have discussed about certain descriptive analysis involving the growth rate, energy intensity and elasticity in order to analyze the growth in energy demand, or generally in order to understand the energy demand. In this lecture, we are going to discuss about two things. One is a decomposition analysis and the second is the parametric approach. So we begin with decomposition analysis. Before we go to the analytical framework, let us look at this diagram. The question that it tries to address is how to study decoupling. Now, what do we understand by decoupling? Decoupling here essentially means the decoupling of growth in GDP from the decoupling of growth in energy demand. So if you look at these two curves, the orange line tells you the growth of GDP in India over time measured in billion US dollar, and this blue line is actually telling you the growth in energy consumption over time, which is measured in terms of kiloton of oil equivalent. So this blue line actually incorporates the use of all kind of fuel. If you look at this diagram, you see that initially both this blue line and this orange line, the rate of growth was almost similar. So they were running parallelly. Beyond a point of time, you see that this orange line is growing much faster as compared to the growth in the blue line. As a result, after a point of time, you may get this kind of a situation. So what is essentially happening? It's like this. Up to this point of time, you see both these curves are going parallel. It means that the rate of increase in energy consumption is almost equal to the rate of increase in GDP. Therefore, if you think about the energy intensity of GDP, that remained almost same up to this point of time. There was almost no change in energy intensity of GDP up to this point of time. However, if you go beyond that, you see that the GDP is increasing at a higher rate, whereas compared to that, the increase in energy demand is lower. So over this period of time, you can expect that energy intensity of GDP is actually falling. It's not staying the same. Now the question comes that if there is an increase in energy efficiency, which is reflected in the decline in energy intensity of GDP, will we be able to reach a situation where our GDP will grow, however, that will not require an increase in the total energy consumption. So with the pool of the same energy, we'll be able to produce more GDP. So at this point is called the decoupling of GDP from energy demand. And if you want to kind of answer this kind of question to understand up to after which year this kind of decoupling can take place, one of the things that becomes very handy is called the index decomposition analysis. We are going to look at this method very briefly and to see some of the application of the index decomposition analysis. So in the basic framework, let us assume that change in energy demand has three common sources. You can assume more than three common sources, but we can start with this three common sources. What are these common sources? The first one is called the activity effect. That is the change in the level of activity leading to the change in energy demand. So if you look at this diagram, we are considering the same economy at two different points of time. At period T1, this is the size of the economy. However, during the period T1, the size of the economy grows. This you can also think it about the size of the GDP. It grows to become this much. So there is an increase in the GDP. Now if there is an increase in the GDP, it is likely that the demand for energy will also grow. So this is one source of change in energy demand, which is captured in terms of activity effect. The second one that we consider here is the change in the structure of the economy. So again, if you look at this diagram, you see it's not only the size of the GDP that has increased, but also the composition of GDP has changed. What is the change? At the initial year, the contribution of the agricultural sector, which is represented by this blue part, was 25%. Same was the contribution from the service sector. So each of these two sectors, agriculture as well as service sector, they were contributing 25% and 25% respectively. And 50% of GDP was coming from the industrial sector. In the changed period, I mean the recent period, you see that there is a decrease in the proportion of share of agricultural sector in the economy. Although you see the size of agricultural sector has gone up from 100 to 150, but the contribution of the agricultural sector has come down to 21% from 25%. If you look at the industry sector, here also you can observe the same thing. So the size of the industrial production, that is the industrial contribution to GDP, was 200 at time period T0, that has increased to 250 in the current period. So the increase is from 200 to 250. However, the percentage contribution has come down from 50% to 36% of GDP from the industrial sector. The third one is the service sector. See, here the growth is huge. Initially it was 100. In the time period T1, it has become 300. So not only the size of the service sector has become bigger from 100 to 300, but the contribution of the service sector has also gone up from 25% to 43% in the economy. Now this is what is capturing the change in the structure of the economy. This is called the structural change of the economy. How the share of different sectors have changed to the contribution of GDP over time. Now, what is the implication of this structural change to the energy demand of an economy? It goes like this. If you think about these three sectors, agriculture, industry and service sector is the least energy intensive sector. So, in order to produce 1 unit of output in the service sector, you require the least amount of energy if you compare it with the agriculture or industry sector. Next comes the agricultural sector, and industrial sector is the most energy consuming sector. So to produce 1 unit of output in the industrial sector, you need much more energy as compared to service sector or agricultural sector. Therefore, if there is a structural shift in favor of service sector, which is happening here, you can expect that other things remaining constant, the energy demand is going to come down. Had there been an increase in the share of industrial GDP, so had the structural shift been in favor of industry sector, then you would have expected that the other thing remaining constant, your energy consumption of the economy would have gone up. So this is the implication of structural change on energy demand. So the structural effect implies the change in energy demand that is arising due to the change in the structure of economy, that is due to change in the sectoral contribution of the economy. The third one is, okay, before we go to the third one, actually one important thing is that when you are doing any decomposition analysis, in order to understand the structural change, it's therefore important that you divide the economy into various parts. Right? Some of the parts are more energy intensive in nature and some of the parts are less energy intensive in nature. And you try to understand whether it's the contribution of the more energy intensive sector is growing, or is it the contribution of the less energy intensive sector that is growing over time. So this is the fundamental thing that you have to do to divide the economy in these two parts if you want to understand the structural effect. The third part is fairly simple. This is about the energy intensity effect. So if the system of production and system of consumption becomes more and more efficient over time, then to produce the same amount of thing, you need less amount of energy. So that is the reduction in energy intensity. So the third source that we are considering, we are trying to understand whether other things remaining constant, this is very important, other things remaining constant, that whether there is a change in the energy intensity which is leading to the change in the demand for energy. So if the energy intensity increases over time, then the energy demand will increase, other things remaining constant. If the energy intensity declines, then other things remaining constant, your energy demand is also going to decline. So let us start with an example and try to see what kind of questions we can answer by the use of this index decomposition analysis. You are already familiar with this particular diagram. Here I have chosen only 3 industries. The aluminium industry, this is the production of clinker for the cement industry, and this is the steel produced. And what we have shown is that the energy intensity in these three industries actually had fallen quite significantly over the years. But now try to match this concept with the concept of decoupling. Now, what we have learned from this slide is that the decline that we have been showing for these three industries captures only the change in energy intensity. But if you think about the industry as a whole, there are other two effects, there are other two sources that can play a role. So the question that we ask is that, okay, we understand that there is a fall in the energy intensity, which will definitely reduce the energy demand, but can this falling energy intensity be able to deliver the decoupling of energy activity growth from energy use in Indian manufacturing industries? So the question is like this, that we understand that due to one source there is a decline in energy demand. However, what is the role of the activity effect and what is the role of the structural effect? So this is the question that we are trying to address here. Now, if you think about the Indian manufacturing industries, what do you exactly understand by activity effect? The activity effect is basically the increase in energy demand or the change in industrial energy demand due to the change in the industrial activity, industrial output, other things remaining constant. What about the structural effect? What I have already mentioned, in order to understand structural effect, you have to divide whatever sector you have into two parts. One is the energy intensive part and the other is the non-energy intensive part. So in case of manufacturing industries, we have taken few industries as the energy intensive industries. They are aluminium, cement, iron and steel, chloralkali, fertilizer, pulp and paper and textile. So there is a reason why these industries are considered to be the most energy intensive industries, because one of the very important energy efficiency policies in India with respect to industry sector is perform, achieve and trade, and under this perform, achieve and trade scheme, which is also called PAT, these are the industries which are considered to be the most energy intensive industries in the first phase of PAT. So we consider that these are the these industries together constitute the energy intensive industries, while the rest of the manufacturing industries, they constitute less energy intensive industries. So when we talk about the structural shift, we are going to see whether the contribution of these 6 industries are going to go up, or it's the remaining part of the manufacturing industries that's going to go up. So this is what we are going to study through the structural effect. Now you can notice that if the contribution of these mentioned 6 industries are going to go up, then due to structural effect your energy use is likely to increase. Whereas if the remaining manufacturing industries output is going to relatively go up, then the energy use is about to decrease. Coming to the last part, this is energy intensity effect. So if the situation for the entire manufacturing sector is same as what we can see in these 3 industries, then of course due to energy intensity effect, the energy consumption is going to come down because the production process has become more and more efficient. But here we are talking about only 3 industries. It has to be true for all the industries, by the way, all the manufacturing industries. So this is how we conceptualize the activity effect, structural effect and energy intensity effect in the context of Indian manufacturing industries. Now let us see how do we do the analysis. Coming to the theoretical formulation, this is one way of doing index decomposition analysis, and this is called log mean Divisia index. What do we do here? We take ET. So what is ET? ET is basically the energy consumption here for the Indian manufacturing sector at time point T. Okay, so T denotes the time period. If I say ET, this is the total energy demand of the manufacturing sector, I can write it as a sum of EIT summing over I, where I stands for a particular industry. So this is a sum of energy consumed by cement industry, energy consumed by steel industry, energy consumed by fertilizer industry, so on and so forth. So this is how I am breaking up the total energy consumption. Further, what I can do is that if I write it as summation over I YT multiplied by YIT divided by YT multiplied by EIT divided by IT, then that again equates to summation EIT. Why? Because if I write it in this way, see, I can cancel out these 2 YITs, I can also cancel out these 2 YTs, and therefore I am simply left with this EIT. So this is the way I can write it down. Now what is the importance of writing down the total energy consumption in this manner? What does it facilitate? It happens in this way. If you break down the energy consumption in this multiplicative form, what you have? You have YT. YT is the total amount which is manufactured by the Indian manufacturing industry. So this is the total output. So one component becomes total output. What is YIT divided by YT? This is the share of production of the ith industry or the ith group, right? So here we have two groups. One is energy intensive and the other is less energy intensive. So YIT by YT actually gives you the share of energy intensive industries and the share of less energy intensive industries. What is EIT divided by YIT? See, this is the energy consumption by the ith group divided by the production of ith group. So you have energy intensity of the ith group. So by writing it down in this way, we have three components of energy demand. And you remember in the previous slides we were discussing that there are three sources of changes in energy demand. These are precisely the three sources. So this will be able to capture the activity effect because this YT is the output. So by capturing the change in output, we'll be able to capture the activity effect. This is denoting the structure, SIT. YIT divided by YT, we are writing it as SIT. So this is giving you the structure of the manufacturing sector. And IIT is the energy intensity effect which we can capture through it. So this is how we are going to write down the equation first. In the next step, what we do, we want to analyze the change in energy demand. We don't want only to break up the energy demand at a particular point of time, but what we essentially want is to understand what the change in the energy demand. So the change in the energy demand over a period of time from T0 to T equal to capital T, this is captured as ET minus E0, which is equal to delta TOT. TOT stands for total. So this is the total change in energy demand is equal to change in activity effect, change in the structure and change in energy demand due to change in energy intensity. So this is the activity effect, this is the structural effect and this is going to tell you about the energy intensity effect. So the total change in energy demand comes from these three sources. So this is one way of writing about it. So this is the additive form. You can also write it in multiplicative form. So ET divided by E0. At what proportion the change is taking place. If you want to write it in that way, then you have to write it in a multiplicative form. So the activity effect multiplied by structural effect multiplied by energy intensity effect. And we will see that actually this delta E activity effect and D activity effect, they look a little bit different. So this is the additive form and this is the multiplicative form. Now we have to see what are the exact expressions for these things, this activity effect, structural effect and energy intensity effect. So what I am going to do is that I am going to talk in detail about the additive form, and the interpretation for the multiplicative form is going to be quite similar and you can do that on your own. Coming to the additive form, if you want to calculate these effects under the additive form, the activity effect, the change in energy demand due to change in activity is given by summation I Wi ln yt by y0. The structural effect is given by Wi ln sit by si0 and intensity effect is given by summation Wi ln iit by ii0. So you can see this change activity effect is telling you the change in output, this is telling you the change in the structure and this is telling you about the change in the energy intensity. Now this Wi is a new term here. How do we write Wi? Wi is basically EIT minus EI0 divided by ln EIT minus ln EI0. So what does the I stand for? So actually in case of this example, you are going to get the value of two I's. So maybe one for the energy intensive sector. So you get a weight for the energy intensive sector and you can calculate the weight for the less energy intensive sector. and then you plug the values of these weights here and calculate what is the energy intensity effect, what is the structural effect, and what is the activity effect. Now, what is the good thing about this kind of log mean Divisia index is that if you add these three terms, you will get Et minus E naught. So there is no remainder which is staying with us. So this is this kind of an additive form. It leaves nothing which is not interpreted. So any change in energy demand comes from either of these three sources. If you want to go by the multiplicative form, then it looks like this. So you see the expression has changed a little bit. Now you have the exponential of this term, exponential of this term, and exponential of this term, and the weights have also changed. For multiplicative form, this is how you calculate the weight. Things will become clearer if we actually go for an example. So we actually move on to an example. Before that, let me just give you a brief background of this log mean Divisia index. This is an index number. This is basically an index number. And before this index number was used to understand the decomposition of energy demand, there was Laspier's index which was in use. But in 1987, Boyd and his colleagues, they wrote a paper on separating the changing composition of US manufacturing production from energy efficiency improvements, and there they used this kind of Divisia index method. After that, there was a regular use of this particular method and this decomposition of energy demand from various attributes. The another important article that can be referred to is by Ong and Louis. So we come back to the example. So this is how the example looks like. So I said that we are going to talk about the decomposition of energy demand in the manufacturing sector in India. And the first thing that we need to understand, how do we define the structure of the manufacturing sector? So you see here there are two rows called group 1 and group 2. So group 1 is energy intensive manufacturing industries, where we have 6 manufacturing industries that we have already talked about. And in the second group, we have the rest of the manufacturing industries, whom we are calling less energy intensive manufacturing industries. And what is the information that we have? We have the information for the year 1990-91, and we also have the information for the year 2010 and 11. So what are the informations? We have the information on energy use and we have the information on output produced for both the years. See, we need three things, right? We need the change in output, we need the change in structure, therefore we need to understand the structure, and the third thing, we need the energy intensity. Now if you have information on energy input and energy use and output, you can derive the other two. What we can do is that in order to understand the structure of the manufacturing sector, you simply have to divide the output of group 1 by total output. So that gives you the structure of the economy. If you want to understand what is the energy intensity, you simply have to, for group 1, you have to divide 5105 by 47563. Okay, so if you are given information on energy use and output, you can derive the structure of the manufacturing sector, and you can also derive the energy intensity of manufacturing sectors. So how do we do that? We come to this particular table after doing all the calculations. So if you see for 1990-91, you have one column. This is telling you what is the total energy consumption of group 1, group 2 and total. What is the output of group 1, group 2 and total, what is the structure, and what is the energy intensity. So how do we make the calculation? Look at this number. This is telling you 36% of manufacturing production is coming from the energy intensive industries, and we have derived this by dividing this value by this value. So this is the total manufacturing production, this is the manufacturing output from the energy intensive industries. So this is telling us 36% is being produced by the energy intensive industries. As a result, you can see 64% is being produced by the non-energy intensive industries in the year 1990-91. Next, if you come to the structure, this value is derived from here. Third, if you come to the energy intensity, for group 1, energy intensity is calculated based on these two values. So this 0.11 is actually 5105 divided by 47563. If you look at the energy intensity of the second sector, this will be 3714 divided by 86342. Okay, and this is the total energy intensity of the entire manufacturing sector. So this is how you calculate the structure as well as the energy intensity. If you have that information with you, now this is easy to calculate. You have to calculate two weights. So W1 is E1T minus E1 naught. So here you have E1T, if here you have E1T in this box, and this is your E1 naught. So here you see E1T minus E1 naught divided by log of E1T minus E1 naught. So this is becoming the weight that you are going to use for your decomposition. Similarly, for the second group, this is for the less energy intensive industries, this is going to be the weight. Once you know the weight, you can easily calculate the activity effect, structural effect and energy intensity effect. So you are going to multiply this weight with log of Yt minus Y naught, which again you are going to get from here. So here you have Yt and here you have Y naught. So this is going to tell you the value of activity effect, structural effect and energy intensity effect. Now again, if you look here, this is what is happening. So these are the changes. So this Yt and Y naught you are getting from here and here. For SIT and SI naught you probably have to go back to the previous table, and energy intensity also you have the figures. Now see what do you need to observe. If you look at the activity effect, it comes with a plus sign. This means that due to increase in manufacturing production, other things remaining constant, the demand for energy has gone up. That is why it has a plus sign. This has a minus sign. This means that due to structural effect, the energy use has gone down. So it basically means that there is a shift from energy intensive industries to less energy intensive industries, structure wise. So the structure of the manufacturing sector has changed in favor of low energy intensive industries. The third is the energy intensity effect. So it comes with a minus sign, and this is a big value. So this means that over time Indian industries has actually achieved a lot of gain as they have reduced their energy intensity over time. So these are the three effects. Now if you add them up, so if you add 22,904 minus 1976 minus 12547, the value that you get is basically 8381. Okay. Now what is this 8381? This is nothing but the difference between the energy consumption at these two different points of time. So what you have done is that you have decomposed the change in energy demand from 17200 to 8819, that is this 8381. So 8381 is the change in energy demand, and you have decomposed the change in energy demand into three parts. The change in energy demand due to change in activity, change in energy demand due to change in structure, and the change in energy demand due to change in energy intensity. So this is how you can carry out a decomposition analysis based on this log mean Divisia index to understand the sources of changes for energy demand of a country or of any sector of the country. For example, we have done it for the manufacturing sector. Similarly, you can, okay, before we go to the multiplicative format, this is how you represent your result. So see, if you add them up, what you are going to get is the figure that we have discussed, right? So here, this value, this 8381. Now I am dividing this 8381 between three bars. So this is the increase in energy demand due to activity effect. This is 22904, right? This is the reduction in energy demand due to structural effect. However, this is quite small. So although there is a shift in favor of less energy intensive industries, the shift is not much. And the third one is energy intensity effect. You can see there is a lot of decline in energy demand because of reduction in energy intensity in these industries. There is another interesting way in which you can represent your result, which is by a stacked diagram. What does this stacked diagram say? It says, see, this is the zero, this is the starting point. It says that Had there been no change in structure as well as in energy intensity, energy demand would have grown by 273% of what it is now. So had there been no change in structure and energy intensity, the energy demand would have been 273%, considering the current change to be 100%. So it would have been more than double the current change. So basically, what is the structural effect and the energy intensity effect doing? They are trying to pull your energy demand down, while the activity effect is trying to push your energy demand up. Now, what is the relative effect of these three sources is finally going to determine what is happening to your final energy demand. So here you see, as a pull factor, the structural effect is contributing, but it's not contributing greatly. It's a small amount of contribution. However, energy intensity gain is actually contributing a lot. So if you actually deduct this 24 and 150 from this 273, or you can say 274 should be here. So this will be 100%. So had there been no structural effect and no energy intensity effect, the energy demand would have been double than what it is now. So this is another way how you can represent this. Let us have a quick look at the multiplicative framework and how we represent that. Here in the multiplicative form, you can see that the activity effect is captured by 6.20, structural effect is 0.85 and energy intensity effect is 0.37. So unlike the positive or negative sign, here we look at whether the value is more than 1 or less than 1. So if the value is more than 1, that indicates that increase in energy use due to this particular effect. So there is a six-fold increase in energy use due to increase in activity. However, there is a reduction in energy demand due to structural change and energy intensity effect. So this actually corroborates the result that you get from your additive framework. And here how you cross check what does these figures mean. If you multiply these three values 6.2, 0.85 and 0.37, what you get is 1.95. So what is 1.95? 1.95 is actually 172.00 divided by 8819. So 1.95 is the proportional increase in energy consumption over the years. So you see the energy consumption has almost doubled, right? So this 17200 is almost double the value of 8819, or specifically it's like 1.95. So this 1.95 is basically the increase in the proportional increase in energy demand, which you should get once you multiply these three effects. How do you represent that? It's usually represented by this kind of a radar diagram, where you see that the structural effect, due to structural effect it's declining, due to energy intensity effect again it's declining, and due to activity effect this is increasing. But they essentially tell you the same story. I mean, if you carry out the additive framework, there is no need to repeat it for the multiplicative framework. It's the same story that is being told. With the help of this kind of an analysis, I'll just brief you about one of the studies. And in this study, what we have taken the same industry group as the energy intensive industries, and the rest of the manufacturing industries were considered as the less energy intensive manufacturing industries. And we have plotted the result of decomposition analysis in this manner. So this is the period 1973-74 to 88-89. This bar represents this period. Then we have 1989 to 90 to 97-98. And the next period is 1998-99 to 2011-12. And what we see here is that, see, the size of the bar is increasing. So the energy demand is growing, and that is obvious. But the interesting fact is that during this 1973, 74, 88, 89, in the early years, this part represents the increase in energy demand due to increase in industrial production. So the push factor was quite important. Whereas you see, there is hardly any pull factor in terms of the gain in energy efficiency or in terms of structural change. If you go to the next period, although structural change hardly plays any role, actually you see a little bit of orange strip here which says that there is a slight increase in energy use due to the structural change. However, you see the role of energy intensity effect increases. So there is a lot of energy efficiency gain, which is reducing the energy intensity of the manufacturing sector, and as a result, the pull factor becomes more important. If you come to this period, you see the activity effect has gone up. However, a lot of the activity effect has been neutralized by a significant gain in energy efficiency. So energy intensity has declined a lot at this period of time. Now, if this is the case, now let us again come back to the question of decoupling. So, what does decoupling mean? The decoupling means that, well, there will be an increase in energy use because there is an activity growth. However, this increase in energy use should be nullified by some pull factors. So, if there is a lot of gain in terms of structural shift and there is a lot of gain in terms of energy intensity gain or energy efficiency, that will be in a position to nullify the increase in energy demand that is arising due to activity effect. That is the whole story. We also tried to understand one more question, that if you actually see the sign of decoupling, you actually see a sign of decoupling. In this phase, hardly anything is being neutralized. Whereas in this phase, a part of energy demand is neutralized. Whereas in this phase, a bigger portion of energy demand is being, increase in energy demand is being neutralized. Now the question comes, from when do you actually start seeing the sign of decoupling? For that, we have plotted the data over the whole period of time. So instead of plotting it for a period of time, this is the year-wise plotting of the activity effect, structural effect, and the energy intensity effect. And something interesting that you can see. See, this black line is giving you the growth in energy demand, total energy demand, without any implication for any effect. So this black line is the increase in energy demand. Here this is the black line, here this is the black line. What is the blue line? Blue line captures the growth in energy demand due to increase in activity. So if you look at this period, that is 73, 74 to 88, 89, you see that this blue line and the black line, they are going hand in hand. So the entire growth in energy demand was due to the increase in activity. So there was no decoupling of energy demand from the activity growth. If you look at this period up to this point, 95, 96, you again see that the blue line and the black line, they are going hand in hand. So again, up to this point, there is no decoupling. However, post 95, 96, you see that the black line has started coming down, whereas this blue line has started rising. This trend becomes even more prominent if you come to the recent period. You see the blue line is rising like anything, whereas the black line is much below the blue line. Why is it that? Because this is the total demand, right? This is the increase in energy demand due to activity. However, out of this, a huge portion has been neutralized because of the gain in energy efficiency. So if somebody asks that, do you actually see a sign of decoupling? The answer is pretty much yes, we see a sign of decoupling in this period. And this is actually one of the very important era in Indian economic history. This is just the post-liberalization period. So you can think that after this point of time, a lot of technology was brought into the manufacturing sector, where these technologies were actually able to bring a lot of energy efficiency, and that can be a cause of decoupling of energy demand from the activity growth. The last thing to observe, you see that the structural effect does not play much role in case of Indian manufacturing sector. So there was not a huge shift either in favor of energy intensive sector or in favor of less energy intensive sector. You can go back to this particular reference if you want to know more about this decoupling story and the use of energy intensity. This is where we are going to stop with the decomposition analysis, and finally we are going to devote some amount of time on the parametric approaches very briefly. Here we will not go into much of the details of the theory, but we'll just see how results can be interpreted when you use certain parametric approaches in order to understand the energy demand. So briefly, what is parametric approach? It goes on like this. We actually try to check the validity of theoretical relationship based on the empirical data. Also, this framework can be used in order to do the forecast of future energy demand. So we take this specific example, and what do we do here? See, on the y-axis, we are plotting energy consumption, right? and on the x-axis we are plotting disposable income. We have already discussed when we were talking about this, the income elasticity. We tried to understand what is the responsiveness of energy demand to income. So we saw that in case of certain fuel, you can expect that there is a positive response. As the income goes up, the consumption of that particular energy also goes up. So you can think about it as LPG, or you can think about it as electricity. So what is this data telling you? So each of these points, they represent one particular household, and they tell you that what is the disposable income of this particular household. So if you take this point here, xi, yi, what is this telling you? This is telling you the disposable income of this particular household is xi, and the energy consumption, you can, as I said, LPG or electricity, consumption of this household is yi. The same information is here for the rest of the household, each represented by one dot. Now, what do we want to do through parametric regression? We actually want to fit one line like this, which captures the average relationship between energy consumption and disposable income. But how do we fit the line? How do we come up with this particular line? See, we come to this particular line by fitting a linear regression equation. And in this framework, we call energy consumption as the dependent variable, and we call x, that is the disposable income, as the explanatory variable. If I actually fit a line, the equation of the line can be represented as y equal to beta naught plus beta 1x. Now, what is beta naught and beta 1x? We'll just look into the next slide. So, beta naught is the intercept term of this line, and beta 1 is actually giving you the slope of this line. So, if I think about beta 1, that is actually telling you what is the change in energy consumption if there is a change in the disposable income. So, the slope of the line tells you the responsiveness of energy consumption with respect to disposable income. Now, coming to the question, how do we fit this line? See, if I think about this point xi, yi, this is the original point that I have. This is the original disposable income and energy consumption of the household. However, when I am fitting the regression line, which is depicting the average relationship, the line looks like this. Okay. So, what I am saying, actually, if the disposable income is xi, that particular household will consume yi amount of energy. But if I try to depict it by the average relationship, it shows that the energy consumption is a bit higher. And this difference between the average relation and the actual thing is called an error, which has been captured as ui. So when we are fitting this line, what we are trying to do is that we try to minimize the sum of square of the errors. So by minimizing ui square, summation ui square, with respect to beta naught and beta 1, we are obtaining this particular line. As we have already discussed that for many of the energy sources, the common sense suggests that as income goes up, the energy consumption of energy resource will also go up. And this is what theory tells us. Now we are going to test it with the empirical data. Now the empirical data will validate the theory if I find that beta 1 is positive and significant. So this is the thing that I have to check for. Since this fitted line is positively sloped, I know that beta 1 is positive. But now I have to check whether this is significant or not. Now how do we understand whether this is significant or not? See, this beta 1, under the hypothesis, null hypothesis that we test, that whether beta 1 is equal to 0 for the population or not, that follows a t distribution. So we try to obtain the t statistic or the t value for both the parameters, for both the statistic beta naught and beta 1. And if I find that the t statistic for beta 1 is the modulus value, the absolute value of the t statistic is greater than 2, that means that beta is significant. Let us now look at a couple of examples. So this is most important. If you get the result of a particular exercise, how do you interpret that exercise within the parametric framework? So this is a study carried out in some part of the world, and the results are a little modified here. They had a lot more number of variables. So we are considering the electricity consumption per household per month in kilowatt hour as the dependent variable. So why is this? So this Y is the electricity consumption, household electricity consumption. What are the explanatory variables? The explanatory variables are family size. So how many people are there in the family, the area of the house, and the income. Now, the electricity consumption per month is regressed on family size, area and income, and this is the result that is obtained. Now, what do we understand from the result? First, we look at the adjusted R square. So, the value of adjusted R square is 0.64. This implies that 64% variation in Y, that is 64% variation in per capita, in per household energy or electricity consumption is explained by the variation of family size, area and income. Okay. So this is the overall goodness of it is quite well. The second observation that we can make, that by looking at these values, so these values in parenthesis, they are telling you the T statistic. So you see only for area the T statistic is greater than 2, which implies area is the only significant variable explaining the per household electricity consumption, and neither family nor income is significant. What is the next interpretation that we have? By looking at this value, this 3.02. So it says that if there is if the area increases by 1 square meter, if the household, if the area of the house increases by 1 square meter, then the increase in energy consumption on an average will be 3.02 kilowatt hour. So this is the interpretation per month. So this is how you can use simple regression equations to understand different aspects of energy demand. The second example, the same kind of explanatory and the dependent variables are used. However, the functional forms are tweaked a bit. So what is here, instead of using Y, that is instead of using the energy consumption, we are using the log of energy consumption. And here you have family as you had, you have area as you had, and instead of using income, we are using log of income. So here now what you see is that other than area, log of income also becomes significant. So income and area, both these variables are now significant determinant of the energy consumption. And what else can we say? Here we can say that if area increases by 1 square meter, then per month energy consumption is going to go up by 0.3%. So notice here I am not saying that it's going to go up by 0.3 unit, but I am going to say it's going to go up by 0.3% because I am using the log value here. Why is it so? You see that if you, or maybe we discuss this and then go back there. So now if we come to the log of income, the coefficient of log of income is 0.02. And the interpretation therefore is, if the income goes up by 1%, then the electricity consumption will also go by 0.02%. So both the things are expressed in terms of percent. So why am I doing so? Because see, if you have a relationship like log of y is equal to a multiplied by log of x, then dy by y is equal to a multiplied by dx by x. So dy by y divided by dx by x, this becomes a. So this, if you can remember, this is the elasticity. This is the elasticity that we have been discussing. Percentage change in y divided by percentage change in x. So if you have a formulation where your dependent variable as well as the explanatory variable both are in terms of log, then this particular coefficient will actually give you the elasticity value. So 0.02 is the income elasticity of energy consumption for households in this model. Coming to the last and final, the next and the final example, this is a result from one of the Middle East countries, and this example we have also used in some previous slides, where gasoline is highly subsidized. So the price of petrol is very low because petrol has been subsidized, and therefore the energy consumption has gone up like anything. Now the government wants to know whether there will be significant reduction in demand for petrol if the subsidy is removed or reduced. Also, they want to know whether demand for gasoline will grow significantly in future as per capita income rises. Following regression equation can answer these questions. What is the regression equation? See, log ET. ET is the energy demand of this country at particular point of time t, right? This is being regressed on log of PT. PT is the price of gasoline or price of petrol at the same point of time. Then you have log of YT. YT is the income here. Don't confuse it with the previous YT where YT stood for electricity consumption. Here YT is the income. So we are taking log of YT and one. So this is the previous year's demand. So this is a lagged kind of a regression model that we are estimating. And what the observations are? See, the observations say that if the coefficient for the price is actually not significant, okay, and you can also say that this minus 0.0817, this is actually the own price elasticity of gasoline in this country, which is not very high, right? Not only it's not very high, the other thing is that it's not significant at all. So even if there is a change in the subsidy policy, even if you increase the, remove the subsidy and the price is increased, it's unlikely to have a great impact on demand. So if you want to reduce the demand of gasoline in this particular country, removal of subsidy or changing the price is not going to give you the result. What will give you the result? You look at this. This is the income. So it says that as income increases, the energy consumption also increases. So income is energy is basically a normal good here and significantly increases. And what is this 0.3736? This is basically the income elasticity of energy demand. Okay. So as the income grows, they will anyway buy more and more gasoline irrespective of what intervention you do in the price pair, whether you remove the subsidy or not. And this is again a significant variable. So obviously the lagged value of the lagged value of energy consumption is going to impact today's energy consumption. So this way it gives you a very important policy implication that price is not really the channel for intervention if you want to get results in terms of reduced energy demand. You have to do it in some other way, because as income increases, anyway the consumption of petrol will increase in this particular country. We are going to stop here. In the next week, we are going to come back with some more topics under energy demand, and we'll discuss some of the policies that are useful and implemented in the context of energy demand. Thank you.